Okay, welcome everyone to the final talk in the Astronomical Observational Techniques and Instrumentation class on the last day. This is very exciting. This last talk promises to be one of the best remaining talks there will be given in this class period, given by Gabriel Guidarelli from the Rochester Institute of Technology. We talk about spectral analysis of white dwarfs.
Thank you for the introduction. As he said, my name is Gabriel Guidarelli, and before I get started, I'd like to thank Dr. Feiger even more for hosting this event. Out of all the hosts we've had, I'm sure he's number one.
That was so good.
And I'll get right into it. I chose white dwarfs for reasons which I'll get into later, but for this title slide, you always need a good picture. This is a Sloan Sky Survey picture, and inside the O is the white dwarf, one of the white dwarfs that I was looking at. Oh, of course. So, just an overview, like all good projects, I started with a question that I sought out to answer. That question changed as soon as I figured out I couldn't answer it, changed a bunch. I'll be talking about, in this presentation, the final question I settled on, how I settled on it, and then on. So I'll begin by talking about planetary nebula and how they form. Starts with a intermediate mass star on the main sequence. As soon as it burns up all its, or most of its hydrogen, it'll start to blow off circumstellar dust, or I'm sorry, blow off its stellar envelope, and form a planetary nebula, leaving a white dwarf in the center burning helium. This is the study of Dr. Eric Blackman at the University of Rochester, and also the study of Dr. Nordhaus here at RIT. He's my advisor, and I thought this is perfect. I could maybe impress him a little bit, maybe get somewhat into the field. So that's why I kind of picked white dwarfs to study. And specifically magnetic fields, because Dr. Blackman at U of R, who was Dr. Nordhaus's advisor, kind of goes up the chain, submitted that magnetic fields inside these white dwarfs, or inside the proto-white dwarfs of an AGB, could be the reason for asymmetries in the nebula found here. So if it was just a star, you might expect it to be spherically blowing off wind, but that is not the case usually. So the question I finally settled on was decided by things I could measure, the rotation speed and magnetic field, or at least I heard I could measure things having to do with magnetic field. I didn't know for sure. So is there a relation between the rotational velocity of magnetic fields and white dwarfs? This made sense because in physics, you expect to see, like, from spinning charges, a magnetic field occur, and it does happen. But you'll find out later, not so much here, and not as you would expect here. So I devised a plan, and it had 5 easy steps. Find a set of white dwarfs, measure their magnetic field, measure their rotation speed, plot the results, and draw outrageous conclusions from these results. So here's a picture of Sirius B, or Sirius A and Sirius B. This is a binary, where Sirius B is the white dwarf. I will not be looking at binaries. This is a filler picture. So the first point on the plan was to find a set of white dwarfs, and for that I have Megan to thank. She pointed me towards the Sloan Digital Sky Survey, and more specifically, Kleinman of 2013 compiled a list of all the white dwarfs in data release 7 of the Sloan Digital Sky Survey. This consisted of 20,000 white dwarfs, and they were sorted by type. Now, what I mean by type is white dwarfs, because they're off the main sequence, have their own spectral typing system, and they're based on the spectral features inside of the spectra. So I was specifically looking at DA white dwarfs, which are white dwarfs that have strong hydrogen features. Like this. This is H gamma and H beta, and H alpha down there somewhere. And note the splitting of the absorption lines due to the inverse Zeeman effect, which I'll get into later. So Sloan gave me this image as a preview for the data that they would give me. Not always, though. They sometimes did not have CSVs to pair with the picture. But when they did, it looked something like this. When I put it into Python, see the H beta and H gamma again. And with this, I was able to find, I loaded it into Python and identified what I called features by fitting it with a black body and measuring what the noise was. And if something was over 3 sigma, I would mark it with a little line down near -5. Units are not really important, log of flux. Okay, so once I had these features, I had to measure the rotational velocity and the magnetic field. So first things first, rotational velocity. And if we all remember Doppler shifting, when a body is moving towards you, the speed of light is still the same, so it must squish the wavelength, and it squishes corresponding to the Doppler shift equation, which if you assume the velocity or the rotational velocity is small, you can just cross out this bottom part, and you're left with the equation to the right, where the shift in wavelength is proportional to the ratio of velocity over the speed of light. So this, let's see. So if I have the change in wavelength, let's see. If I have the width of the spectral features, I can find the velocity of rotation. And the reason why you get a width or a lengthened spectral feature is because you're setting the spectroscope over the whole star, and so you're getting blue shifted and red shifted areas of the star. So going back to this plot again, I simply just went to each feature and coding, not in real life. I looked for the full width half max of the peaks, and I used that to compute the effective shift and therefore the velocities with outrageous uncertainty, as the variance across the spectral features was large, which is the case for many of the literature I found, or much of the literature I found. So I have rotational velocities, and next on the list I had to measure magnetic fields. And now I bring up inverse Zeeman scattering, or the inverse Zeeman effect. So inverse because instead of up, these are absorption features, so they're down. Zeeman because they're splitting. Due to the magnetic field, it's stark if there's the electric field. And effect because that's at the end. So it all starts with the perturbation to the Hamiltonian of the quantum state, as found by Zeeman himself, Peter Zeeman. So when you take this and assume that B is going in the Z direction, I'm not sure if that's a fair assumption, but it at least makes it simpler. You can take out the vector stuff, the dot product there goes away. And if you take the expectation value of the Hamiltonian, you have the energy here. And simplifying the whole equation, you end up with 4 pi mc over the charge of an electron with dE and lambda, which you can measure. So now I have a way to measure both the magnetic field and the rotation velocity. I'm left just with the plot, the results. You see velocity on this axis. Note the sign of I, because we don't actually know the inclination of the stars. We could be seeing it head-on, which would yield a velocity of 0, or we could be seeing it flush, which would yield the maximum velocity. So these are on the order of kilometers per second, and they are comparable to literature I found. Most that use this method are consistent with 0. And there are ways to get better values, but they rely on different data, more time series data. And we have B field across here. These are lower than what I found in literature by about an order of magnitude or 2. And that could be the assumptions I had made in the previous slide having to do with the Zeeman effect. For that derivation, you have to accept that the field, the magnetic field you're applying to the system is small compared to the magnetic field of the atoms themselves, so fine structure doesn't play a role. Fine structure being orbit spin interactions as well as relativistic effects. So, as you can see here, I was going to suggest at the very beginning that for larger velocities you'd see larger magnetic fields because you get more spinning of charged particles, but that's not the case, if anything, here. Drawing wild conclusions, it looks to be a downward slope with a larger magnetic field producing a smaller velocity, or vice versa. So, in conclusion, this is inconclusive. The data set was far too small and the uncertainty was way too high, but I could do better. This is things to be learned here. So if you all want to do this at home, I can send you the link to the Vizier database containing the SDSS data. And so the question answer is no for now, but you guys can answer it on your own time. Places to improve are both the measurements in rotation velocity and magnetic field. Astroseismology is a great way to measure the rotational velocity. So this is just looking at how the star wiggles in time, and based on that data, you can come up with a rough estimate for the speed at which it's rotating, and that has to do with the G-mode oscillations, which is the gravitational restoration forces of the hydrodynamic equilibrium that you have when you hit the star in a simulation. Let's see, but this requires time series data or very, very high spatial resolution, which is probably not possible right now. These, to the right, you see P-mode oscillations, because I could not find a picture of G-mode oscillations, but they look roughly similar. It's just a wiggly shape on top of a sphere. Another place to improve is different methods to measuring the magnetic field. Here is a plot by Warner, 1990, showing different transitions or absorption features as a function of magnetic field. And if you note, the regime I was looking at was around here, where you get many, 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 many degenerate states. So I was assuming a weak field when really I should have been looking very deep into the quantum mechanics of this situation. But I'm an astronomer, I don't have to do that. Another method to do this is to look at the polarization of the star, and the circular polarization of the star should be a function of the wavelength, which is a function of the magnetic field. There are sources for looking at that instead. So, in summary, the rotation of white dwarfs may be related to the magnetic field, but more data is needed. Their astroseismology could improve velocity measurement. Higher order corrections and polarization data could help with the magnetic field measurements. And with that, I'll open to questions.
Okay. Okay, great. Plenty of time for questions. Mm-hmm. Go ahead. Victoria.
Okay. Was it hard to separate, or did you think about having to worry about separating the spread in the Zeeman effect in the rotational?
Yes.
Because of rotational properties.
So that was something I thought of a few days ago after measuring a lot of things. But if you'll notice here, delta lambda as a function of lambda is proportional to some constant, so it's a linear trend with wavelength, whereas this one is not linear with lambda. So I have 3 points available of alpha, gamma, and beta. I can look at how those change with wavelength and see if a magnetic field is playing a role in widening the feature, I guess is the best way to tell it, because it may be 3 features.
Do you mean alpha, beta, gamma, and hydrogen lines?
Yeah, so she was asking, how do I know that it's widening due to spinning around rather than widening due to a magnetic field?
Okay, great.
Can you go to slide 12? Is MG just like mega Gauss or something?
Oh yeah. I'm sorry. I just changed that right before the talk. I wasn't sure.
So I guess my question is your error in velocity. So for some of those points it drops below zero. Does that mean that some of these could necessarily be going in the opposite direction than the value you have? If it's a negative velocity?
Well, you'd see the same thing. With, like this way is the same as this way inside the spectrograph, because it's not distance you're seeing. It's rather wavelengths. So if it's traveling one direction with some velocity, it's the same as traveling the other direction with some velocity. You'll see the same features.
Right. Well, the positive numbers aren't going away. Like one's not going away and one's not coming towards.
Correct. Yeah.
Yeah. So if they fall into the negative number, and originally you think it's going away, it could necessarily really just be coming forward based on these error bars.
So it's independent of the direction of omega, I guess is the best way to say it.
Okay.
Oh well, besides the sine theta part of it.
Isn't this V the rotational velocity?
Correct. Yeah. So
Okay.
I'm saying the
That-
redshift.
Well, no, but
That helps things.
yeah, it's
Oh,
rotational
okay, okay.
velocity.
Sorry.
So negative is nonsensical.
Correct.
Mm.
Thank you. That's it.
More questions? Could you go back to the slide with Sirius? I'm not joking. There it is, right there. I always wondered, is it dwarfs or dwarves?
I would say dwarfs.
I don't know.
Dwarfs.
I'm not sure
That was
either.
with an
It's with a V.
Is it?
Never mind.
Really?
Oh,
I
did
think
I
it's
spell
dwarf.
it?
Difference. If you're talking
It's
about like
dwarf.
the
No,
dwarves,
stars is
spoken
dwarfs.
realms is a V, but I think these would be.
I think they're dwarves for that Disney story.
Seven dwarfs.
Yeah.
Give it a Google.
What did you do about Stark broadening?
Stark broadening due to
Yeah.
the electric field. I
Yeah.
did not consider that.
How would that change your results?
Let's see. So. The electric field, let's see, I would expect that to be perpendicular to the direction of travel of the particles. I'm trying to think like it, because it goes back and forth between what's causing what to happen.
So it sounds like you're not sure.
Yeah.
Okay. Does the distribution of the magnetic field strength matter? And what I mean is on the, let's see.
Like, be it on the poles or.
Well, if you have, yeah, I mean, if you have, you know, that's the rotational axis, right?
Mhm.
And I guess it's a dipole field, is that the model?
Yep.
And
Suppose I like that was the conclusion I was drawing at the very beginning, but if it's not a rotational, it's not being caused by the outer rotation, then I don't know what the field could look like.
so
But it's integrated anyway.
So the local, so the effect that you're measuring in the spectrum is due to Zeeman scattering from material that's generating the photons, right? So it's from the emitting region. So it's the local strength of the magnetic field in the emitting regions. That's what's contributing to the spectrum, right?
Yeah.
Right.
So it's emitting different photons per region.
Right, so the emitting regions are all over the disk of the star.
Yep.
Right, and so the local strength of the magnetic field is different in each of these.
Mhm.
Is that right?
Yes.
So is it more intense here?
So-
The field lines come together?
Are you asking where the magnetic field is?
Well, does the magnetic field strength vary across the
Oh
disk?
yeah, of course. As it does on the sun. That's why you get sunspots.
So you're now inferring the strength of the magnetic field. And what does it mean to say the strength of the magnetic field if it varies over the emitting region?
Strength of the magnetic. It's the net magnetic field because it's integrated over the whole star. That's what you're looking at.
So when you say net, might you be implying an average?
Yeah, for sure.
And if it's the case that certain regions like on the sun are hotter than others or having a burst, if they happen to have a higher magnetic field than the others, then it's sort of the intensity weighted average of the magnetic field across the emitting region.
Yes.
Okay, I think that's all I had. Any more questions? No, okay, let's thank Dave again.